Hello, I'm Mark Warner, founder of Warner Advisors, a consulting firm formed to help biotechnology clients take their process from concept to commercial operation. Welcome to the series Understanding Advanced Biotechnology. This is part two, project development.
So first, a brief refresher from the series overview. Below is a project execution timeline. As you remember from the overview, I discussed both the traditional approach and the expedited approach. This is that expedited approach. It has the same components as the traditional approach, just optimized to deliver a project on a shorter timeline. So as we look at this, you will see in red the development stage, stage one, which involves FEL1, FEL2, and FEL3. It's this development stage that we're going to talk about during this portion of the series. What is included in the development phase of the project? This is the phase known in the engineering industry as front-end loading, or FEL. This is a terminology that discusses a basic technology and how that develops a concept to what it would look like at a commercial scale facility. It then leverages that concept to generate both capital cost estimates and a detailed project timeline. It does things like identify a site for the project. It also provides enough engineering detail on the process to generate a budget grade estimate that can receive board, bank, or federal loan guarantee approval. That's a key point to note here. At the end of the development phase, or what's known as FEL3 as the completion, that's the level of detail that a bank or say a USDA loan guarantee or a DOE loan guarantee would require to be able to fund that project. So let's discuss more the FEL phases and key criteria. The table below will give a brief summary of the different components of the various FEL phases. I'm going to cover this fairly quickly. Please realize significant detail will be provided on each of these in the following sections. So FEL1. FEL1 is the business planning stage to define the concept. The documents that are generated in this are a basic block flow diagram of your process, a rough material balance of your process, and what we would call an order of magnitude cost estimate. This work generally takes in the range of 1 to 2 months to complete, and realize that the cost estimate generated usually only has an accuracy of about plus 40%, minus 25%. FEL2 is the scope development phase. It's the early phases of engineering, and it's when budgetary equipment estimates are developed. The key documents that come out of this phase are process flow diagrams, a much more detailed heat and material balance, process layout and site plan, what your process will look like on a piece of property, equipment specifications, and budgetary quotes for your key equipment. This portion of the process usually takes 2 to 4 months and will generate a capital cost estimate in the accuracy range of plus 25%, minus 15. FEL3 is what's called the project planning or basic engineering package stage. This is a much more detailed stage when you look at how your process fits on a specific piece of property and you generate items such as the process and instrumentation diagrams, a detailed site plan, you obtain firm equipment quotes at least for your key equipment, you have a detailed understanding of all the utilities you're going to use, and you have enough detail of engineering to be able to estimate quantities of piping, concrete, and other items. This will usually take in the range of 4 to 10 months to develop, and will have a capital accuracy in the range of plus 10 to minus 5%. Now this FEL3 is very important as this is the level of detail required for a bank loan or a federal loan guarantee, say a DOE or USDA loan guarantee. So if you're thinking of financing your project through any of these three mechanisms, it's very important that you understand this is the level of engineering detail that will be required. I've seen entities often develop these loan guarantee packages only to be disappointed after having paid a large fee for submitting the application to find out their engineering detail was not sufficient to be selected or moved forward. So if you're going down one of those project financing routes, it's very important to understand this process. As I noted earlier, I believe it's important to be able to give real-world examples of what engineering work products look like. Unfortunately, most engineering work products are covered under client non-disclosure agreements to where you can't use any of that information. A good source of what some of these engineering work products look like were some reports put out by the National Renewable Energy Lab, or NREL. They've done some benchmarking studies on both economics of what it would take to build various cellulosic ethanol technologies, and some evaluations of different gasification technologies. These are very important in that the process followed is very similar, at least to the FEL1 and FEL2 process. And a lot of the deliverables used in these documents look very much like the work products you'll get if you hire an engineering firm to do your development. So because of that, and I wanted to give attribution, I'm going to be using examples extracted from these two public documents, which you can see here, that I will use throughout the process as examples. So let's move into a more detailed discussion of front-end loading, or FEL1, which is the concept development phase of the project. So if I'm ready to move into the FEL1 process, what am I going to need? First, I'm going to need a description of my entire process, from the feedstocks I'm going to use all the way to the product I intend to make. I'm going to need a design basis. What do you need the process to do? Very often this is a capacity. I expect it to make X tons or pounds per year of a certain product. That will become the basis of the project. I'm going to need some lab and pilot data on the key processes, be it fermentation or some of the separation equipment. To be able to start this engineering process, we're going to need at least some key data to be able to help us size the equipment. We're also going to have to understand the expected customer specifications. What are we trying to make and at what level of purity? This will be very key in helping us develop the process. So if I look at the dimethyl glop process I discussed previously, we'll do a brief review. We're going to make material by fermentation. We're going to clarify it. We're then going to purify by crystallization, dry, and package. So if this were my process and I was taking this into FEL1, what would I need? First, I would need the basis we discussed. How big is this plant going to be? What is our expected capacity of our product, and what is that specification? In this case, it's going to be a technical grade dimethyl glop, and I'm assuming that that technical grade dimethyl glop is already defined by the industry as far as what the contaminants and level of purity are. Next, I'm going to have some rough idea of the efficiency of our process. In this case, we'll assume we have enough data that already tells us we're going to generate about 0.4 pounds of dimethyl glop per pound of sugar used. It's also going to tell us that once we make the dimethyl glop, based on some of our preliminary lab data, we already know that we're going to have recovery in the range of 92%, meaning for every 100 pounds of dimethyl glop produced in the fermenters, we're going to get about 92 pounds of that out as final product. And finally, if I look at data, I don't in FEL1 have to have data for the entire process, but I usually have to have it at least for a lot of the key processes. In this case, it would be fermentation, clarification, and crystallization. One of the first things clients usually want out of an FEL1 analysis is an order of magnitude capital cost estimate. This can be somewhat difficult because the process at this point has a fairly limited level of definition, but there are ways to get at least an order of magnitude cost estimate. The most likely way is by benchmarking against other similar processes. And what do I mean by this? Well, what I mean is if you have another similar fermentation process with similar equipment, centrifuges and crystallization, if you have information on that, you can commonly use what's called the rule of 6/10 to at least get an order of magnitude estimate. So let's talk about what that means. So what that means is the capital cost of the plant I'm trying to build will be represented by the capital cost of this reference plant, the plant that we have some information on, based on a ratio of the two proposed capacities to the 0.6 power. So let me give more definition. For our dimethyl glop process, we found a similar process that makes 300,000 pounds a year, and we found out that that facility cost about $10 million to build. So based on that information, we know we're trying to generate our capital cost. The reference plant costs $10 million to build. We know our proposed facility, we're looking to make 2 million pounds a year, and the reference facility is a 300,000 pound a year facility. So we take that ratio, and that ratio to the 0.6 power times the cost of the reference facility gives us an order of magnitude cost estimate. This rationale has been proven over 50, 60 years of process data, often used in pulp and paper, some biotechnology in the petrochemical industry, and has been found to give a good rough order of magnitude early phase capital cost estimate that at least gives you a placeholder to give you an idea of whether your efforts are likely going to be in the right economic range. Now let's talk about what that actual cost means. So we have that estimate of 31.2 million for our proposed process. What that means is the most likely cost is 31.2 million, but it has a level of accuracy, this range of accuracy I discussed in the table above, of plus 40% minus 25%. Or put in real numbers, it means that while 31.2 million is the most likely cost, the range we're projecting is anywhere from a low of 23.4 million to a high of 43.7 million. Capital cost estimates. Let's take a quick moment here for an aside on capital cost estimates and some thoughts I have from spending many years generating those estimates and seeing how those flow into actual facility construction costs. First, capital cost estimates, I believe in my mind, are some of the least understood and often misused information within advanced biotechnology. I generally find that the misuse of this information is not intentional, it's just a basic misunderstanding of what the numbers represent and what their accuracy is and how those numbers can and should be used. So in the case of FEL1, it's an order of magnitude estimate. It's only used to determine roughly whether the project you're looking to build is going to be in the right economic range to be viable. For every cost estimate you give, and this is something I think that's very important, you shouldn't just give a cost of a facility, the $31.2 million I discussed on the previous slide. It always has to be accompanied by a rough scope. That cost represents this size of facility, a 2 million pound per year DMG facility. It should also have a level of accuracy, in this case, say plus 40% and minus 25%. And it also has to have some key assumptions. In the case of our dimethyl glop process, we've assumed that the wastewater we generate will be able to go to a local wastewater treatment utility. That's not the case, and we have to build facilities on site. That's going to have a significant capital cost to it. So it's very important every time we quote a capital cost estimate that there's at least some basic context that goes along with that estimate. And it's important for those estimates generally to represent some of the items that are the highest cost impact on your company pro forma. As you develop your techno-economic model, you'll understand what the highest risk factors are, and those should really be the assumptions that are quoted with each of your capital cost estimates. So I'm going to use this point to give one of the home renovation analogies. How does FEL1 compare with a contractor coming in to look at, say, a kitchen renovation in your house? You bring in this contractor and you're going to describe what you're trying to do. We're going to knock out these countertops, put a new fridge in there, do this work over here. After listening and walking around, the contractor is going to tell you, well, based on what you've told me and having built similar houses like this, it's probably going to cost about $30,000. Could be as high as $40,000, could be as low as $25,000, but it's really going to depend on the appliances you pick and how you want them laid out in the end. FEL1 is really no different. It's a good faith, best effort estimate of what it's going to take to do that project, but you have to be careful in the level of accuracy because until a lot of the key decisions are made, it's not going to be a cost estimate that has, frankly, a real high level of accuracy. So let's move into the front-end loading 2 or FEL2 stage, which is known as scope definition. So FEL2, what will you need? If you're moving into FEL2, we have the assumption that the information generated in FEL1, including the order of magnitude cost estimate, were at least sufficient to make management feel comfortable that more work was warranted to take the concept further. So first thing you're going to need as you move into FEL2, where FEL1 is very high level, FEL2 is going to have to start to look at what's it going to take to put your process on a specific piece of property. So the assumption is in FEL2, you're going to start looking at specific sites. So you're going to need going in a short list of potential sites that you've dealt with different state or local agencies to identify, and you're going to have to know key information like how much the land is going to cost you, how much utilities are going to cost, and if they're available, whether you have a host that's going to charge you fees, and what permitting will look like. You're going to need budgetary estimates for your key process equipment. So as we develop the process more, for each of these key pieces of equipment, the fermenters, the centrifuges, the crystallizers, we're going to have enough technical information to deal with vendors to be able to get at least a good quality budgetary estimate for that equipment. And you're going to have data for all your proposed processes. And it's going to have to be much more significant data for your key processes. So back to our block flow diagram below, and you'll see the basic information represented below, including the lab data and the rough overall yield information that we had in FEL1. So what kind of additional information is going to be required in FEL2? If you look back at the previous slide, you'll notice I've included the lab data. I've moved it over to include drying. I've expanded the areas of the process. You're basically going to have good information pretty much over all of your unit operations. You're also going to have things such as the wastewater we talked about earlier. We've made the assumption that the local utility can accept the wastewater in FEL1. As we get into FEL2 and look at specific sites, we're going to have to talk to the actual wastewater treatment entities and determine if they can take that level of wastewater load and what it's going to cost us. And items such as the drying and the amount of water that's going to be dried off, which is going to go into the atmosphere, those are going to start to be important, as those are going to be things that drive things like air permits. So you'll see an expanded level of data that's going to need to be required as you get into FEL2. So what is a heat and material balance? This is a term that's used within the process industry a lot, and there's not always a great understanding of what that means. So let's take this drawing that I've taken out of the NREL report. I do realize you're not going to be able to read the detail at this level of resolution, but wanted to use it as an overall example, and we'll drill down further. So you'll see on this diagram, there's some key components. First, there's detailed chemical compositions on the left, and I will show you these later in detail. Each one of the streams on this diagram has a number which then ties to the table below, which gives a detailed chemical composition. Over on the right, you'll see that for each key piece of equipment, there's corresponding information which talks about its size and specification, things you would talk to vendors about what's needed for that specific piece of equipment. So what I'm going to do is drill down in this red block area to show you a zoom in of what that equipment information is going to look like. So here is the close-up process detail. You'll see each piece of equipment is numbered and tied to the equipment on the top of the drawing I discussed, and each process stream has a number that ties to the table at the lower left of the drawing. In this case, for example, glucose feed to the process is stream 401. Now if we move on to the process table, you will see that that stream 401 ties to component 401 on the stream table. To represent the stream on the drawing, this gives a total flow, the insoluble solids, soluble solids, temperature, pressure, vapor fraction, water, and individual component. In this case, we noted 401 was glucose, and you'll see that basically it's 100% glucose. For other streams on the table, you'll see things like contaminants and other additives added. This is very critical in developing this overall heat and material balance. For each component and for each contaminant in the process, you're going to have to be able to do an overall material balance. And as you go through things like heating and cooling and phase changes, you're going to have to also be able to do an overall energy balance to be able to determine things like natural gas and electricity and the utilities you'll need to run your process. Since we are talking about site-specific implications, the engineering design will also need to include a site plan. This is a basic layout of the facility, including buildings, roads, where tanks and the major process components will go. This is important to help with the cost estimating. For example, the ability to estimate things like pipelines will depend on how big the facility is and how far the tanks are from the process. So this basic site plan information is very important. One, to make sure the piece of property you're looking at will hold your process, and also to be able to generate enough information to get a more detailed level of cost estimate. So at the FEL2 level of engineering, we move to a different technique of generating a more refined cost estimate, which is often called a factored cost estimate, where in FEL1 we factored an entire facility to generate a order of magnitude cost estimate. Within FEL2, since we have more process information, we build up a budgetary equipment list and we use that equipment to develop a factored estimate of the cost of the process. So here's what that would look like. For each one of the key unit operations, we generate a detailed equipment list, and with working with vendors, we come up with at least a budgetary cost estimate for each one of those pieces of equipment. In this case, it will be fermenters, centrifuges, crystallizers, dryers, and the packaging system. Given the numbers of each one of those pieces of equipment and cost, we develop a total budgetary equipment cost. In this case, we're projecting that the dimethyl process will have roughly $8.75 million of equipment that go into that process. So, based on that total equipment cost and what's called an installed equipment factor, that helps us develop a more refined level of estimate. Very commonly within the biotech, at least advanced biotech industry, the common factor is roughly about 3.5, meaning the total cost of the overall facility will generally be about 3.5 times the cost of equipment developed at the FEL2 stage of engineering. So in this case, for our dimethyl process, the 8.75 million of equipment multiplied by 3.5 comes up with roughly a cost of $30.6 million for that process. Now it's important to note here, the level of accuracy of this FEL2 factored estimate is generally seen to be in the range of plus 25% to a minus 25% level of accuracy. So the other documents that will be generated through the FEL2 process will be process flow diagrams, the detailed heat and material balance that I reviewed earlier, a site plan showing in detail how your proposed facility is going to sit on the proposed site, a detailed equipment list that has at least rough utilities. It's very important to understand how much power, steam, and other utilities all your equipment is going to need to be able to generate an accurate capital cost estimate. You're going to have a project execution schedule discussing how you're going to buy the equipment, install it, and start it up, and what that looks like in a detailed schedule. And it's important to coordinate with your company pro forma. Make sure that as you learn more items as you go through various phases of engineering, that you feed that information back to your company pro forma and make sure what you're telling investors and outside groups is consistent with what you're planning for the engineering of your facility. That you need to make sure that the site is represented correctly in that analysis, and you also have to evaluate the differences between a greenfield build or a hosted site. Greenfield being where you have a vacant piece of land and build your entire process yourself. A hosted site, say you build your fermentation facility next to a corn wet mill where you get your sugar, that often has very significant benefits as far as capital cost because you can get your sugar over the fence. They can often provide you power and steam. You can send your wastewater back to them. While it has many capital benefits, it can often come with a significant host fee, and you have to be able to weigh the benefits and downsides of each of those to determine what your best approach is. So as we wrap up FEL2, let's go back to the home renovation analogy and see where FEL2 fits within that. So in the case of FEL2, it's when you bring the contractor in and you know the layout of the kitchen you want, you've selected the appliances you want, but you still may be considering options for cabinets, countertop, and flooring. So based on that information, the contractor is able to revise their information to give you a little more accurate cost estimate. They're going to tell you in this case, they believe the cost is going to be about $29,400 based on your appliance selection and based on allowances they've made for flooring and countertops. However, until you actually select the flooring and countertop, they can't give you a real firm estimate. This is a good analogy of where FEL2 fits based to a home renovation. So we'll now move on to the front-end loading or FEL3 phase, which is the budget approval phase. So what information will you need to complete FEL3? Detailed information on the site, including survey, proposed lease, and purchase agreement. This is important because to be able to do the level of engineering required, you're going to need all this detailed information to be able to understand utilities, permitting, site layout, and be able to develop the quantity information needed for cost estimating. You're also going to need fully integrated pilot data. In earlier versions, I've shown where key information is going to be needed to get budgetary estimates on the equipment. In the case of FEL3, the level of engineering detail required is going to require data not only from running the different unit operations, but running them as a fully integrated unit so that there's time for impurities and other materials and recycle stream to work through and generate representative data. You're also going to need key information from the landlord on utilities and regulatory agencies to make sure all the utilities, power, natural gas, water, things you're going to need to run your process, that those are there in reasonable supply and that the process you're looking to build can make it through the regulatory hurdles. This will help you generate firm estimates for key equipment and get budgetary estimates for the remainder. Just remember, the goal of FEL3 is to make enough engineering detail to make the project site specific and to be able to estimate quantities of piping, concrete, and other materials to be able to generate a much more accurate capital cost estimate. One key concept to understand when discussing FEL3 is the concept of balance of plant. I'll use the aerial photo below of a commercial scale factory to make the distinction. First, what's often referred to as the core process, also known as inside boundary limits or ISBL within the process industry. That refers to the core process of a project or a facility. In the case of our dimethyl glop, that's the items referenced in those blocks on the block flow diagram. Then we come to the concept of balance of plant, also known as outside boundary limits or OSBL in the process industry. And that's referred to as everything other than the core process. In the case of most facilities, that's items such as raw material storage, product storage, rail in and out of the facility, laboratories, office buildings, utilities such as boilers and transformer yards. It's everything you need to facilitate the core process. And one thing that's important to understand is that balance of plant is typically the majority of the project cost. And I know that's a concept that's often hard for many developers to understand initially with their core process. They're very familiar with their core process and what the equipment costs. They're often less familiar with that kind of balance of plant and what it costs to put in tank farms, rails, and utilities, and unfortunately find out it's the majority of the cost of a commercial project. So let's discuss the focus of FEL3, moving to the site and the full process evaluation. So as we work through this, we're going to look at items such as utility access, power, water, wastewater, how those are serviced to the site, whether they're adequate, and if not, what we need to do to make them adequate. We're going to look at roads and building infrastructure. What do we need for office buildings, laboratory, maintenance buildings? We'll begin early phase permitting for the environmental permits. This will help in determining whether our process is going to need costly emissions controls and other items. We're also going to expand the engineering beyond the process to look at items like civil, structural, mechanical, and electrical. These are items outside the core of the process, but things that are very important to getting the facility built and developing cost estimates. We're also going to make it a priority to generate enough engineering detail to make quantity estimates for things like concrete, pipe, and other things. It's important to understand in FEL3, while you're doing some design work, it's only enough design work to be able to get quantity estimates. The drawings generated will not be able to be used for construction, and there will be a much more detailed phase of engineering that comes in the next scope of the project. Now, we're also going to have to look at the process and get a little better definition. This includes things like instrumentation pumps, storage tanks. It's also going to move from the block flow diagram I showed you earlier to what's called a process and instrumentation diagram. So where the block flow diagram was really just one page with an overall heat and material balance, something like the process flow diagrams and the detailed P&ID. The process flow diagrams for a dimethyl glop process would probably be about 3 pages, but as an example, the P&IDs would expand to such a detail, those drawings alone would be probably 20 to 30 full-size drawings, just delineating how the equipment is set up and how the instrumentation, piping, and valving all relates to one another. So you've heard me discuss detailed equipment bids previously, and I want to give an example of what an equipment list looks like. This is one that was extracted out of the NREL gasification report that I discussed earlier. So the key information you're going to need in this case are things like a description of the equipment, the quantity, how many of them do you need, the cost of the piece of equipment, how much it weighs is very important, the size and capacity. In this case, this capital cost estimate was based on an FEL2 level of engineering, so they had not been able to define things like all the size and capacity of the equipment, the pressure rating, what the horsepower of the motors, what the RPMs of the motors are. Those are things that an FEL3 estimate would require to be completed. So let's discuss how we generate a capital cost estimate based on FEL3 level of engineering. First, it's important to understand that it's generated bottom up from estimated quantities of things like piping, concrete, steel, valves, and not a top-down factor like it was in FEL1 and FEL2. We're going to use the equipment cost from discussions with vendors and the estimates for the piping, steel, and concrete to generate what's called a direct total construction cost. It's important to understand this is not the overall project cost, just the direct construction cost. We need to consider what are called indirect or often called soft costs, in that they're outside of construction. The major portions of these often include engineering, which typically runs 8 to 12% of the direct construction cost, construction management, 3 to 5%, procurement, 1 to 2%, contingency, which we'll discuss some later, is usually in the range of about 10%. There's also costs for permitting, taxes, and other owner costs, such as in-house engineering, land costs, and those items. So based on that description, let's take our dimethyl glop process and look at what an FEL3 capital cost estimate would look like. First, we come up with our equipment, piping, and other costs. This will be the direct construction cost. For each one of these categories, equipment, piping, structural, electrical, each one of these would have spreadsheets below it making calculations. In the in the equipment category, each one of those pieces of equipment would have detailed information, cost, similar to what we showed in FEL2. But in the case of piping, each major pipeline would be broken down by diameter of the piping, material of construction, an approximate length, and they would use industry factors to come up with costs for what it would take to install that. So as we add up each of these categories, we come up with what's known as a direct construction cost. In the case of this project, roughly $22.6 million. Then we do our calculation of indirect costs, the engineering, procurement, construction management, permitting, and other items we discussed in the description on the previous slide. Finally, those both add together to come up with a total project cost of $29.89 million. This would be our reported FEL3 cost estimate for the dimethyl glop process. So just to give perspective, let's review our dimethyl glop process against the FEL phases we discussed earlier. In this table below, the first three columns, the phase, the description, and the documents, all have remained the same, but let's talk about some ballpark costs and accuracies. So in the case of FEL1, which if you recall was going to take a month or two to do, that would probably cost in the range of $10,000 to $25,000 if you went to an outside engineering firm to do that level of analysis. As we discussed previously, that's going to be in the range of a plus 40 minus 25 capital cost estimate. For the FEL2 phase, that's going to cost in the ballpark for a $30 million facility like dimethyl glop as a reference, probably in the range of $100,000 to $250,000 for the FEL2 level of engineering. As discussed previously, it's going to have a cost range of about plus 25 to minus 15%. And for the FEL3, which we just showed the completion of, that would cost for a similar process somewhere in the range of probably $750,000 to $1.5 million to complete the FEL3 work. It's going to have a capital cost accuracy of plus 10% and minus 5%. That's important to reference in the previous estimate of the $29.89 million, that's going to have that level of accuracy of plus 10%, minus 5% if the engineering detail meets the standards outlined here in FEL3. This is a good point to discuss what contingency is and what it's not. Contingency is an allowance that's added to the budget for known but undefined costs that are within the scope of the project and some allowance for unexpected conditions that are likely to arise. It is fully expected that you're going to spend the contingency within the scope of the project, and that's important. As we look at the level of engineering that's done for FEL3, we noted it's enough engineering to get quantity estimates, but it's not the complete engineering. As you complete the engineering, there are going to be identified smaller but significant costs that will add up and come in under the contingency. So now is an important point to talk about what contingency is not. What it is not is a slush fund for new capabilities. I often see ventures put a 10% contingency on a project, which is appropriate at the end of FEL3, and make the assumptions that they'll be able to do upgrades to their process or new allowances or things that are outside of the project, and assume that is simply a buffer in case of the unexpected, when most history of how projects are developed and executed tell you that items will come up, especially on new technologies, that will require that to be spent within the scope of the project. So I strongly encourage you, when budgeting your project, do not assume you'll be able to spend any of that contingency on anything outside of the original scope of the project. So let's get to our final phase of home renovation analogy for FEL3. FEL3 is the equivalent of when you're able to tell your contractor the exact layout of the kitchen, you've selected all the appliances, cabinets, countertops, and flooring, and the contractor is able to give you a firm price and a firm schedule. It doesn't mean there won't be unexpected conditions that could come up, but based on the information your contractor has, They believe they have enough information to give you an estimate and a schedule that they can deliver. So let's talk about the manner in which a startup can control their project costs. It's pretty much inevitable within the industry. The capital cost is going to end up being in a range that you want to get down either for your own needs or for those of your investors and how much you can fund. So what are really your options? The real option within your control is scope of the project. You should focus all your areas on scope, scope, scope. What is truly required of the project and what is a want? If you look at the difference between, say, a must in a project and a want, must being a minimum functional requirement to meet your design standard versus a want, which is functionality, optionality, maybe ways you'd like to run in the future, but you're not sure you need, those can often drive a project cost up 30 to 50%. The other thing is, I often find people trying to make assumptions that they're going to be much more efficient than standard process construction of, say, chemical plants and refineries when building their facility. Unfortunately, there's usually factors like expedited schedules and the fact that you probably don't have a really strong balance sheet compared to a lot of the large companies building facilities that are going to make it hard for you to be that attractive to a construction contractor. I'm not advising that you shouldn't try and be more efficient in this area. I'm just advising that history tells me those that have assumed they're going to save money here generally haven't and can run into budget problems. So let's talk about examples of what should wait for the second version of a plan. First are lower quality feedstocks. You often have built your process based on high quality feedstocks out of something like a corn wet mill for sugar, and you'll often find in discussions you can get cheaper, lower quality feedstocks from those or from other sources. Unfortunately, that generally has a lot of flow-on problems within the process, where to use a lower quality feedstock, you may need different processes or more refining downstream. That can add a lot of complexity and a lot of cost, and I encourage clients to save that for the second plant. Another item is often internal water reuse. Again, it's obviously going to be great to reuse as much water as you can. Take some of that wastewater, clean it up, maybe use it back in your fermentation. That can be both capital intensive and complex, and worry about recycle of different contaminants and things that'll cause a complexity, again, I think should wait for the second version of the plant. And finally, a high degree of heat recovery. Obviously, being in the industry of advanced biotech, we want to be as energy efficient as we can. Trying to integrate a high level of heat recovery in a process can actually cost a lot of capital, and it can also give a degree of complexity that can make a project hard to start up. All of these items on the bottom are items that will be easy to retrofit or get cheaper funding for once your core technology is proven. So I always advise my clients, focus on the minimum scope first, get that plant up and functional. Once that happens, it's going to be cheaper and easier to get money to add these items on. So I've talked about the ways to work through the development process from FEL1, FEL2, FEL3, some of the implications on how you can control cost. So let's talk about some factors to look out for. What I talk about is where the wheels can come off. Unexpected items that are big enough that they can cause a real problem on the project, and these are things you should make sure you have a handle on before you get too far. Most of these generally are what I would call the more boring non-process items. By nature, most startups have spent so much time on their own core process, they have a pretty good idea of what it will do and how it will scale, but there are other secondary items around this balance of plant concept that can often be budget breakers. First one is poor site conditions. If you're trying to build, say, near water, near a dock, to be able to ship your material out by water, it's very common that the site conditions will be very poor. You may need to put piling or stabilization under your equipment and buildings, and I've been involved in many projects where that piling or stabilization can amount to $2, $3, $4, $5 million. Definitely something that can negatively impact your project, and it's something you should have a handle on during the engineering stage. Availability of utilities. Utilities, if you're using a lot of them, power, gas, and other things, can be quite expensive to bring into your site. So determining if you have ample utilities and an ample allowance as you start up and may change your process, that can be very important. The regulatory environment. What permits will you need and how easy is it going to be to get them? This is something that you need to seek some permitting advice early in the process and get a good assessment of what's the likelihood that you'll be able to permit your facility and make sure there's not going to be any onerous conditions that will keep you from running that plant cost effectively. Transportation access. This is really going to depend on your type of materials and really the value of your materials. For lower cost commodity materials, the transportation could be quite a big deal, especially if you're looking to ship by water or rail. There's a lot of expensive infrastructure that can come with that, and that's something that has to be known up front. And finally, if you're doing a project in a foreign country, there is risk around currency exchange. I will never tell people that they shouldn't do a project in a foreign country. I've done many myself. All I advise people is know the risk up front. And if you're working in a foreign country, that currency exchange can be significant. I've seen currency shift over 50% over the life of a project from the time it was approved to construction, and that's something you need to make sure you have mitigation for. I want to thank you for listening to the second part of the series, Understanding Advanced Biotechnology Commercialization, where I reviewed the project development phase. My contact information is below, mark@warneradvisorsllc.com, or you can find more information at warneradvisorsllc.com. Thank you.